Hi, I'm Aki Fujimura of D2S. I'd like to talk today about the 50 nanometer point for mask making being the tipping point for requiring context-sensitive, simulation-based mask data preparation. So I'd like to start by talking about the layout which we used the simulation for to demonstrate that 50 nanometer is the tipping point for context criticality. The layout below is showing that there is a line and space patterns, 10 lines, and then to the left is completely exposed, that 100% those, and to the right is completely unexposed. So we have the lines in varying contexts going from left to right, going from high dose surrounding it to low dose surrounding it. Okay? So what we would like to demonstrate is how the lines on the left versus the lines on the right change as the line and space decrease from 300 nanometer down below 50 nanometer, where we can demonstrate that we have context dependence. That is, the left one turns out differently from the right one. So here are some of the simulation results going from 300 nanometer line space all the way down to 30 nanometer line and space. These are results from assuming that the combined blur combination of the eBeam based Coulomb blur and also the process based blur, the combination of the two being about 30 nanometer. So assuming that, the results of the simulation done by Johan Choi of D2S demonstrates that at 300 nanometer you can see, you kind of get what you drew, right? You draw a rectangle, you get a rectangle. At 100 nanometer, you start to see some corner rounding. By the way, these pictures are proportionately blown up. So obviously, 100 nanometer line and space is 1/3 of 300 nanometer line and space. But if we did that, you wouldn't see anything on a 40 nanometer version. So, so we are blowing up the picture so that they look like they're the same size, but in fact, they're much smaller. 70 nanometer gets more corner rounding, and by 50 nanometer you can see that there is significant line length shortening, and 40 nanometer it's even more, and by 30 nanometer it pretty much disappears. Blowing up the 40 nanometer picture because I want to show you the context dependence. So this shape, as you remember from the first slide, the left side is 100% exposed, right side is 0% exposed, and that context matters to how these line and space patterns prints. That's what's important. So the leftmost line is getting fatter than the middle lines. The rightmost line is getting thinner than the middle baselines, and it might be hard to see visually, but the leftmost line, it has a significantly longer line than the rightmost line, and so on. So again, it's context dependent, right? So just looking at the 40 nanometer rectangle, 40 nanometer wide rectangle, doesn't tell you what's going to happen when you try to print that on the mask. You need to look at what's around you to know how it's going to come up. That's the context dependence. And because the context, context in this case is very simple. You have, either line and space next to you, or you have 100% next to you, or you have 0% next to you. It's very extreme to demonstrate the case. But in the real design, the context is very, very complex. Even before you get the complex shapes, they're complex, and when you get the complex shapes, they're really complex. So you can't do rule-based analysis to do truly context-specific analysis. So in the world where context matters this much, you have to do simulation-based processing to know what's going on. So that's the main point about 50 nanometer. At 50 nanometer, it's kind of actually already questionable. 40 nanometer, it's definitely context specific. Now, the world of mask making knows this already, and there's a kind of a chemistry answer to that, which is that you would use slower resists. Slower resists take longer, and slower resists take higher doses to print. But if you use slower resist, you can do better. So as opposed to the 30 nanometer combined blur that we were assuming before, here are some simulation results for 15 nanometer combined blur, which is probably the best you could do right now from a chemistry point of view. So if you compare the 30 nanometer, it's pretty clear. With 30 nanometer blur, you can't draw 30 nanometer lines, but with 15 nanometer blur, you can do that. And you can see that the line end pullback on 40 nanometer is significantly improved by using the 15 nanometer blur. Another thing that's important, you could argue even more important than how the contour is expected to turn out, is how the contour is expected to vary when you print it multiple times. So this is a very extensive 1,000 epoch simulation, a Monte Carlo simulation that shows what happens if you vary the threshold amount by some probability and random probability distribution, and how does the 15 nanometer blur situation do compared to 30 nanometer blur situation? You can see that the up and down variation in the height of the blue variation is significantly more in the 30 nanometer case compared to the 15 nanometer case. And that is demonstrating that CD variation or line edge roughness or other measures of manufacturing goodness, manufacturing stability or reliability is significantly improved by using the 15 nanometer blur. Now, slower resists have limits too. So more simulation of smaller line and space patterns show that once you get to 20 nanometer or 15 nanometer, without further manipulation, things don't really show up. But at 25 nanometer, which is kind of hopeless with our 30 nanometer blur, things are still at least printing a little bit, but you can see a very high degree of context dependence. The leftmost line versus the rightmost line is visibly very different, both in line and shortening, and also in the width of the line that would print. So here again, context dependence. Now, it might look like at the 30 nanometer blur, the left one and the right one aren't that different, but actually they are quite different. And also at 40 nanometer, it's quite different. So even at 15 nanometer blur, 50 nanometer line and space is the limit if you care about 2 nanometer precision on mask making, which I think most people using 15 nanometer blur cares about 2 nanometer precision on the mask. This chart is showing the context sensitivity in line end shortening too. The top set of lines are showing how context sensitivity, that is the difference between the leftmost line and the rightmost line in terms of line end shortening, happens below 50 nanometer. The bottom pair of lines is showing that if you use a 50 nanometer blur, then the divergence visually starts at 40 nanometer. But if you care about 2 nanometer precision, it actually really starts at the 50 nanometer point. But below 40 nanometer, the divergence is very, very quick. And you can see that in the simulation of the nominal contour plots that are demonstrated in red underneath. Line number 1 is the leftmost line, and line number 10 is the rightmost line. Now, one thing you can do to correct for this is dose-based correction of the mask shapes. So in this case, we are studying what happens with dose-based correction with changing to make the line width as uniform as possible. You can see in yellow that the rightmost variation and the leftmost plot shows that there's a significant difference there compared to what's happening in the middle. If you do traditional MPC, mask process correction, by changing the shape, you can do that, especially for width correction. You can do that, and you can see in blue that you can make the up and down variation of the blue line much more uniform from the leftmost to the rightmost. But you can improve the contrast, which directly translates to CD uniformity and line edge roughness improvements. You can improve it the best if you do dose-based correction, as you see in the green on both the plot and the contrast dots down below. And when you do the similar simulation-based analysis, the set of pictures on the top, which are the raw pictures that you saw before, compared to the result of dose-based correction, the dose-based correction version shows up a lot better, and you can see that the variation on 25 nanometer, for example, is much improved with dose-based correction methodology. Here again, this kind of dose-based correction must be done in a simulation-based method, not a rule-based method, because context sensitivity starts to dominate at sizes below 50 nanometer. So what happens if you don't have context sensitivity, or if you don't have simulation-based mask data preparation or mask verification, is you're forced to choose between two evils. You have either to live with conservative design rules, just in case the context is the worst possible context. You have to make the design rule for all situations uniformly conservative. Just in case it's bad, just in case what's next to you is the worst situation, you have to make it bad. And that is the situation that really the world faces today. But the mask shop cannot say to the OPC shop, you can't print 40 nanometer features. Most of the time it prints fine, so you should be able to do that. Well, then what happens is the situation on the right, where you have mask hotspots. On occasion, you have that context-sensitive bad spots, and even then, not all instances are going to be bad, but probabilistically, some of those are going to end up being a mask hotspot, and they end up escaping the mask shop without simulation-based context-sensitive analysis or correction. So to conclude, I believe simulation is the future of mask data preparation. Dose modulation-based correction provides the best solution, but in any case, no matter what you do, you have to have context-dependent correction or simulation for verification. And we think that context dependence indicates a simulation-based solution to be the best solution. Thank you.